What's up guys, it's me Sir Ernest, and today we will talk about the motion of particles in a coordinate system that is both translating and rotating. So consider a two coordinate system. One is fixed, let's say here, with origin O, X, Y, and Z axis. And let's say this coordinate system move here, and while translating in this direction, it also rotates. Let's say at this point, this is where the origin of your moving system O prime. Let's say aside from translating, it also rotated like this. Okay, so here we define several vectors. First one is the position of the origin of the moving frame. Let's call that R, capital R. Okay, and then if we have a particle, let's say here, that particle has position vectors with respect to the fixed frame and the moving frame. So with respect to the fixed frame, the coordinate system, the position of this particle would be R, and this will be our R prime system. Okay, so here we define the following. The velocity of the prime system is now given by V, and this is equal to R dot naught. So therefore, the velocity of the particle with respect to the fixed frame V prime is now equal to V is now equal to V prime plus omega cross R prime, which is what we got earlier, plus the velocity of the translational velocity of your moving frame. Now, on the other hand, the acceleration of this particle in the fixed frame is a combination of the acceleration of the particle with respect to the moving frame, with the rotating frame, plus omega dot cross R prime plus 2 omega cross V prime plus omega cross R prime. So we notice that this has been determined last video, which pertains to which results from the rotation of your moving frame, and then we just add the acceleration, the translational acceleration of your moving frame. So here we have several terms. We have 1, 2, 3, 4, and 5 terms. So if you are in the moving frame, okay, you are going to experience a person outside from your moving frame in the fixed frame will observe your acceleration according to this equation, wherein this person will detect 1, 2, 3, 4, 5 acceleration terms. So we already know that a prime, small a prime, is the acceleration of your particle in the moving frame. So if we're going to measure this is something that is physical. This term, this term, this term, this term, or this, and this term are your inertial terms. So you're already familiar with this inertial term. This inertial term is the acceleration brought about by the translational acceleration of your moving frame. And these three other terms is brought about by the rotation as seen in the terms wherein your omega is present. Okay, these three terms have their special names. This term is what we call omega dot cross r prime is called the transverse acceleration. Okay, so this acceleration is essentially a result of any angular acceleration of the rotating system. Okay, so if the rotating system, if the axis of rotation and the angular velocity of your part of the rotational system changes, transverse acceleration will be present. This term, on the other hand, is what we call the Coriolis acceleration. The Coriolis acceleration appears whenever a particle moves in a rotating coordinate system. Okay, so if the if the moving frame is rotating, given by omega, and the particle is also moving with respect to that frame, Coriolis acceleration is observable. And lastly, this term is what we call the centripetal acceleration. Because remember, this is being observed by an inertial frame. So in the inertial frame, you will be able to notice the centripetal acceleration given by this equation. Yes, this is the same centripetal acceleration that you learned in your Physics 1. And this is experienced by a particle being carried around a circular path for a fixed r. So if r changes, that means there will be a v prime. Therefore, aside from your centripetal acceleration, Coriolis acceleration will also be observed. This term, the centripetal acceleration, is always directed towards the axis of rotation and is perpendicular to the axis. So for example, these terms, how are these terms related in terms of direction? So if this is your omega, okay, and then let's say omega speeds up, or assume that omega dot is parallel to omega and omega dot is positive. So that means omega dot positive is the speed of the axis of rotation increases. Okay, so again, this is your omega dot. Okay, so let's say this is your particle. So this particle is, let's say, moving in this direction. Okay, so the r, let's say this is your origin, this is your r prime. Okay, so if this is your r prime and this is your omega, and then this is your omega dot, so your transverse acceleration, green, will be the cross product between omega dot and r prime. So in this case, that is tangent to this path. This is omega dot cross r prime. That's why it's called transverse acceleration, because this is the acceleration perpendicular or tangent. This is the acceleration tangent to the circular path. So sometimes we call this your tangential acceleration in your Physics 1 class. Next would be your Coriolis acceleration. if the particle, let's say, is moving away, for example, say this is the radius. So let's say this particle is moving away from the axis of rotation. Okay, so this is omega cross v prime. So that means this will accelerate. Okay, again in the as observed by an inertial observer, or an observer in the inertial frame, that will follow the same direction as your tangential acceleration. Okay, this is 2 omega cross v prime. And then lastly, your centripetal acceleration. So omega cross r prime would be this direction, right? Because omega cross r prime is in this direction. So therefore omega cross r prime is in this direction, which is what we expect for when we have a centripetal acceleration. It's pointing towards the center of this circular path. Okay, so that's it. Those are your inertial terms. Again, this term, this A naught term, capital A naught term, is the acceleration of your translational acceleration of your moving frame. Okay, so in the following videos we will have several examples to describe this motion. But for now, thank you for watching, and I'll see you guys in the next video. Bye bye.